Hello everyone. Today I'm with you a concept related partial differential equations. Today's topic is one dimensional heat equation. We will see derivation part of one dimensional heat equation in this video, and I will introduce another video uh, solution part of the heat equation. If you are watching my video first time and if you have not subscribed my channel yet, subscribe this channel to get more videos which I am going to upload further. As well as if you like this video, please give like button in the YouTube channel. Now, to derive this heat equation, first let me recall some fundamental principles involved in the heat conductions. The first one is heat flows from higher temperature to lower temperature. It is very common phenomenon. Even heat flow from a hot place to cold place. Second one, the amount of heat in a body is proportional to its mass and temperature. So whenever there is large mass, heat also the amount of heat stored also more. Similarly, whenever temperature is there, the heat stored here also more. So this also common phenomenon. Third one, the rate of heat flow across an area is proportional to the area. That means whenever area is more, the heat flow also obviously more, and one more factor is there, and to the temperature gradient normal to the area. These three principles are very important to derive the heat equation. Let me introduce this diagram. Consider a homogeneous bar of uniform cross-sectional area A. Cross-sectional area means this one. For example, this is one cross-sectional area. So its area, cross-sectional area is A. And let the sides be insulated. So both sides here, this side as well as upper side be insulated, and take one end of the bar as the origin. That means this is the origin and this is the this one is x-axis. So we have kept one end at the origin and the direction of heat flow as the positive x-axis. So here we assume that heat flows from left to right, that means in the positive direction of x-axis. Now let us consider a small portion of this this bar. That means let us consider a slab of thickness delta x. So this is our slab which we are considering for our derivation of heat equation, and this is length, that is delta x length, and R1 is the heat inflow to the slab, and R2 is the heat outflow from the slab. And this point in the x-axis is the x, and being this length is delta x, so this point is x plus delta x. Now let us consider some more definitions or points. Let rho is density of the given material, and S be the specific heat, K be the thermal conductivity. Also, U of xt be the temperature of the slab at a distance x from the origin. Now, let delta U be the change in temperature in a slab of thickness delta x. That means the slab which we considered there, delta U means that is change in temperature. And now let me write mass of the element. So how to write mass here? We have density as rho, and we know that definition for density. So density D is equal to, we know that this is equal to mass by volume. So mass can be written as m is equal to density into volume. So here we have density into volume. Here we have density. So density is rho, and volume of that small thickness. What is that? Here cross-sectional area is A, and that small slab is having thickness delta x. So area into thickness will give us volume. So m is equal to density into volume. So m is equal to rho into volume is A into, that is area into delta x. Therefore we can write mass of the element as A into rho into delta x. This is what the mass of the element of small thickness delta x. Now, so as we already discussed the three important concept fundamental principles, here let me consider the second one, second concept principle. Amount of heat in a body is proportional to its mass and temperature. So amount of heat in a body is proportional to mass and temperature. Let me use this concept here, this principle. So therefore the quantity of heat stored in this slab element is S into A rho delta x delta U. How we get this one? So we use here the amount of heat stored in a body is proportional to mass. What is mass? Mass we have A into rho into delta x. Here temperature we already assumed as or considered as delta U. So mass into temperature is, it is A into rho into delta x into delta U. So this is the proportionality. So heat stored is proportional to mass into temperature. But to eliminate this proportionality and to bring the equality, we know that we are adding one constant there. So heat stored is in a slab is equal to bring the equality, we have added constant of proportionality, that is S, where S is the specific heat which we already introduced. So constant, that is S into mass into temperature. So mass is A rho delta x, temperature is delta U. This is what the quantity of heat stored in this slab element means, the small portion of slab element which we considered. Now, hence rate of increase of heat in this slab element, rate of increase or rate of change of this heat in this slab element, that we denote it as R, is equal to S A rho delta x, being it is rate of change dou U by dou T. Let me mark this as equation number 1, and we will use this equation in the next upcoming steps. Now, as we already discussed or recalled three fundamental principles, the third one we will be recalling here. The rate of heat flow across an area is proportional to the area and to the temperature gradient normal to the area. So let me use this concept here. So we will recall the diagram also. Here R1 is the heat inflow and R2 is the heat outflow for this small slab which we considered of thickness delta x. Now R1 is rate of heat flow inside and R2 is rate of heat flow outflow heat. Now R1 or R is proportional to, from the principle, so here it is proportional to area, that is A. So R1 is proportional to A into temperature gradient. If you consider R1, so this inflow, so this point, that is a starting point, this x coordinate is x. Therefore the temperature gradient at this point is dou U by dou x at x. So R1 is proportional to A into dou U by dou x into x. So to remove proportionality and to bring the constant, to bring the equality, we just add the constant k here. So R1 is equal to A into dou U by dou x at the position x. But here minus sign is added. This minus sign because always heat flows from higher temperature to lower temperature. In this diagram, so we considered heat flow from the left side to right side. So whenever heat inflow is there, that is R1, so it is coming from, this heat flow is from higher temperature to lower temperature. Therefore, R1 we write it as equal to minus K A dou U by dou X at the position X. Similarly, R2. Here R2 means heat outflow and this point is X plus delta X because this length is delta X. At this position X plus delta X. So temperature gradient is dou U by dou X at the position X plus delta X and area is A. So R2 is proportional to A into dou U by dou X at the position X plus delta X. So we eliminate or we remove the proportionality and bring the equality by adding the constant K. So that is R2 is equal to minus K A dou U by dou X at the position X plus delta X, minus sign due to fundamental principle 1 which we discussed, that is heat flow from higher temperature to lower temperature. This constant K is thermal conductivity which we already introduced here. Now from equation 1 and 2, equation 1 we have written for R. So and from equation 2 we can write total heat stored, that is or rate of change of heat inside the small thickness, that is R1 minus rate of change of heat inside the slab is the heat which enter minus heat which flow out. So that is R1 minus R2, that is what the rate of change of heat here inside. So R is equal to R1 minus R2. We already got an expression for R that is written in equation number 1, and here in equation 2 we have R1 and R2 expression. We rewrite and substitute. R is equal to S A rho delta X dou U by dou T is equal to R1 minus R2, which we write it as Ka dou U by dou X at the position X plus delta X minus Ka dou U by dou X at the position X. Here both side A is common, so that we can cancel A and we simplify. Dou U by dou T, let me keep left side only, and the constant S and rho and S, again S, K and rho and S, let me shift to the right side so that we get dou U by dou X at the position X plus delta X minus dou U by dou X at the position X divided by delta X. Now here in this diagram we have considered slab of thickness delta X. Now we take the limit delta X is tending to 0, that means delta X is very small tending to 0, applying the limit. So we get dou U by dou T equal to K by rho S, that is constant, into limit delta X tends to 0 dou U by dou X at the position X plus delta X minus dou U by dou X at the position X divided by delta X. And in the next step we replace this K by rho S as C square, we write, and also this limit, this is the definition of second order partial derivative. Here in the function place we have dou U by dou X and the variable change is for X, therefore this definition is for derivative of dou U by dou X, partial derivative of dou U by dou X, that is this limit definition will be replaced by dou by dou X of dou U by dou X, that is dou square U by dou X square. So dou U by dou T is equal to C square into dou square U by dou X square. So this is from the definition of the second order partial derivative. This is nothing but one dimensional heat equation. Watching.